Okay, so let's get started. Before we start the actual lecture, I have a few announcements. So you all received an email and a PIM from Ping Pong about this, but the schedule has changed a little bit due to guest lectures that were harder to schedule, and a few mistakes I made also, so I can't just blame the guest lecturers about this. But anyways, there is an updated schedule at TimeEdit. And that is the primary source of the information for the schedule. I tried to copy all that information into Ping Pong, but of course there could be mistakes in Ping Pong, and if there is, TimeEdit takes the priority. Also, be a little bit careful about rooms, because rooms will be slightly fluctuating. So you will mainly be in this room and mainly be in EL41, but there are changes to the smaller changes to this. Then also I would like to say, which I forgot to write here, that on Thursday I will meet, after the lecture, I will meet with the student representatives for the first time. So if you have any feedback, constructive criticism, please feed them to them or directly to me if you like. And we still have time to make changes if possible. Okay, so with that, let's get started. We talked about last week, we talked about the physical layer, so we finished off that, and then we started to talk about codes, binary codes, mainly for error detection, but possibly also for error correction. So just to review a few things here, there is some input and some output to this one. We have k bits in, and we have n bits out. N is greater than k, and the rate, which is k over n, is therefore less than 1. This is the special case. There are cases when n and k are equal, but they're not those super interest for us, right? Then there are the coded bits, and they are the output here is called the code word. The input is called an information word or information bits, information blocks, same thing. There is a notation here, the code, and the code is the collection of all possible outputs. So that's the code. A systematic code have code words of a very special form, where the k first bits is the input to the encoder. So these are the information bits, and then there is check bits or parity bits at the end, and there are n minus k of those. Okay, so k information bits and n minus k parity bits, because this one is a n-bit vector. Okay, so that's the general setup. And then we use different types of block encoders for different purposes. The main purpose in this course is to do error detection. So we would like to design this such that we get good error detection. We'll talk a little bit what that means in a while. And then otherwise, in general, we would like to keep the code rate as high as possible, because that means that we add as few as possible of the check bits. Okay, and the check bits is only there for error detection. They serve no purpose for the layer above, except that it enables us to do reliable transmission. So it's overhead in a sense. We would like to limit the number of check bits for the same performance, of course. Okay. Then some other things. Hamming weight is the number of ones in a binary vector. Hamming distance is the number of positions in where two vectors differ. Okay. So with the Hamming weight between two binary vectors u and v, we can find that with the Hamming weight of u plus v, where this plus here with the circle is modulo 2 addition. So if two bits, a bit in a position in u and v are different, then this will result in a 1, right? If two bits differ, when we add them together, we get 1. If they're the same, we get 0. So this basically then counts the number of positions in which u and v differs, and that's exactly the Hamming weight. The minimum distance of a code turns out to be important. So what is the minimum distance? Well, we look at the Hamming distance between all pairs of code words, and we find the smallest of those distances, and that's the minimum distance. So we need to look at two different code words, otherwise the Hamming distance between an object and itself is 0, so that doesn't count here. Okay, so if C is then the transmitted code word, the received bits we get at the receiver is the transmitted code word modulo 2 added with the error pattern, where the error pattern has ones in the positions where there are errors in transmission. So then the Hamming weight of the error pattern is the number of errors that occurred in that code word. So E here will change from transmission to transmission, depends on the noise on the channel and so forth, right? And we would like to look at Y and figure out whether there is an error or not. Okay, so the receiver only knows Y. The receiver also knows C, or basically the principle for how encoding was done. So here, I mean, this is the main principle of error detection. Okay, so this is something, a big take-home message. How do we do error detection? Well, we look at the received pattern. We get a bunch of bits. And then if those bits corresponds to a code word, we think things are okay. If it's not a code word, we're sure it's not okay, because what was transmitted was a code word. So if it's not a code word, errors have occurred. If it is a code word, then we think it's okay, but we're not guaranteed to be correct in that assumption. Okay. So for a code word with minimum distance d min, it turns out that we can find all error patterns with weight less than d min. So if d min is 7, for instance, we can find all error patterns with 6 bits or less. Okay. This turns out to be important if errors are randomly distributed and rather unlikely, which is the typical case when we do transmission, because then patterns with low error weight are more probable than patterns with higher high weight. Okay, so if C is the transmitted code word, then for all C's in the code, we say that E is detectable error pattern. If it is so that if we take a code word plus E, it will not be in the code. Okay, so basically it's like this. If we have the code words like this, then an error pattern like this that will never take one code word to another code word is detectable, while a code word which takes goes from one code word to another like this is not detectable. So undetectable, detectable, and these are detectable. Okay. So when we have this minimum distance, if the weight of the error pattern is less than the minimum distance, basically we cannot go far enough from one code word to get to another, and therefore we guarantee to find all those errors. While if the pattern is longer than the minimum distance, we might get unlucky and then end up at another code word. But we could go in a safe direction and be okay, right? But if we want to put some guarantees, this is a guarantee that we can actually state, and it will be correct. So basically, we would like to have a code with high minimum distance. This is typically a design goal. We would like that also to have good burst error correcting capability. We haven't really talked about what that means, but you can read about that in the book. And then a good ability to detect completely random bit error patterns also, which would occur, for instance, if you have a hardware failure or something like that. Then the bits you read out of a memory or something like that is completely corrupted. There is no particular idea that fewer errors are more likely than many errors. Okay, so if this is what we would like to have in a code, then of course a good code should be here. A good code is something that has high rate, which means low overhead, and low complexity for doing encoding, and low complexity for detecting errors. So the receiver complexity and transmitter complexity should be low. So these are typically engineering things, right? Okay, and then codes in common use that we talked about is single parity check codes, internet checksums that we talked about, and today we will finish off the cyclic redundancy check codes, and that will be it for this course. Of course, this field is immense in itself, if you like, so you can study this in great detail if you like. Okay, any questions before we continue? Okay. And just to be clear, we want to do error detection because we would then like to do that the receiver can figure out that the bits the receiver got are in error and can request a retransmission of this. And we will talk about retransmission protocols a little bit later today. Okay. So to talk about CRCs, or cyclic redundancy check codes, these are typically described in terms of division of binary polynomials. So a binary polynomial is a polynomial with binary coefficients. And a binary polynomial can represent a bit pattern by where the coefficients in front of various powers of x indicates in which position bit is a 1. So maybe before even going to the general case here, it's easiest maybe understood in a example. So if we have a binary vector G, which is 1, 0, 1, 1, for instance, we see we can think of this as a polynomial where these are the coefficients in front of the variable in the polynomial. And the variable, let's call it x. And x serves no other particular purpose in this course than just to be a placeholder. Okay. So then it's the only decision we need to make is to say, okay, so we have 4 coefficients here. So we need a degree 3 polynomial to do this, right? We need the constant term, the coefficients in front of x, x2, and x3. So then the only decision we need to figure out is that x3, is it here or here? Is it to the left or to the right? Okay, that's the only thing we need to do. But we need to decide that and then stick to that. Otherwise, we will be in trouble. Okay. So in this course, let's do this to say that this is the coefficients in front of x3, this in front of x2, this is in front of x, and this is in front of x0, which we then just write as 1. Okay, so then this polynomial will be then 1 times x3 plus 0 times x2 plus 1 times x1 plus 1 times x0. Or if we just simplify this, it's x3 plus x plus 1, like this. Okay, so in the general case then, if we have a polynomial of degree n minus 1, then this corresponds to an n-bit pattern. Okay, so we need a degree which is 1 less than the number of bits we want to represent. Okay, now we will look at polynomials of the sort x raised to a power times a polynomial like this. So x, say x squared times g of x. And then if we look at the bit pattern which this corresponds to, let's just first write out the polynomial and then identify coefficients. So then this will be x5 plus x3 plus x2, right? I just multiplied x2 with g. And this then corresponds to a bit pattern which is equal to, we have a 5th degree polynomial. So how many bits can we represent with 5 bits for degree 5? 6 bits. Okay, so we need 6 bits here. So let's just start from the left here. So it's 1 because it's x5. There is no x4, so that's 0. We have an x3, so that's 1. We have an x2, which is 1. And then we don't have an x1, so that's 0. We don't have an x0, so that's 0. Sorry. We just wrote out the pattern here. Right? And now we see that the first parts here, the first 4 bits, is the bits that we had here. Okay, so that corresponds to the bits which was represented by the polynomial g of x. So by multiplying a polynomial with x to some power, we add the number of zeros here, which is equal to the power that we multiplied with. So 2 here means 2 extra zeros. Okay, so far? All right. So now, when we then want to add polynomials with each other, that is done modulo 2. Okay. So if we have a polynomial x3 plus x plus 1, and we want to add that to the polynomial, let's see, x4, x3, and then plus 1, like this. Okay. Here, and here is maybe confusing in the beginning. Here we have regular plus here to separate the powers of the in this polynomial. But when we add 2 polynomials together, we add the coefficients correspond, in front of each of the corresponding powers. And we need to do that modulo 2 because the coefficients are binary, right? It's a binary polynomial. So the addition here is modulo 2. Okay. So how is this done? Well, let's write this out. We have here x4 plus 0. Okay. So what do we have in front of x4? Well, here we have 0, and then modulo 2 addition to 1, because we have an x4 at the second polynomial, like this. X3, we have 1 x3 here and 1 x3 here, so it's 1 plus 1, modulo 2 then, x3. x2, we don't have an x2, so it's going to be 0 times x2. I'll just write it out for completeness. Do we have an x? Yeah, we have an x here. 1 plus 0x. And then we have a constant term, 1 plus 1 times 1, like this. I just took the corresponding coefficients in front of x4, added those, modulo 2, and did that the same for all the powers. And then at the end of the day, we have here x4, no x3 left, no x2, because we didn't have any from the beginning. We have x left, and that's it. Okay, and if we want to convert this back to a vector, since we have a degree 4 here, we need 5 bits. Okay, so it's going to be 1 for 4. There's no 3, no 2. There's 1x, and there's a 0 constant term. So that's the vector corresponding to this. Of course, we could have done this addition right away by looking at the bit patterns rather than the polynomials. So if we write out the bit pattern that corresponds to this, it will be 1x3. Oops, we need to start with x4 because that's the highest power here. So we have, if we look at this, it will be 0. We have x3. We don't have an x2. We have an x. And we have a 1 like this. And that should be modulo 2 addition with the pattern corresponding to this term, which is an x4, no x. There is an x3, there is no x2, there is no x, but there is a constant term, 1, like this. And then if we do modulo 2 addition to this, it's the same thing. There's not even a carry here, right? We do this term by term. So it's modulo 2 addition 1, 1, it's 0. 1, 0, it's 1. 0, 0 is 0. 1, 1 is 0. 0, 1 is 1, like this. Okay, and hopefully, yeah, it turns out to be the same as when we calculated this as a polynomial. All right? Questions so far? No. Okay, so these binary polynomials is just a convenient way of organizing calculations when it comes to binary vectors. It's nothing more magical about this. So people then ask, so what is x here? Don't worry about x. It's just a placeholder for keeping track of where the bits are supposed to be ones, and where it's basically telling you in what position. The power of x will tell you in what position there should be a 1 in the corresponding bit vector. Has no other meaning at this point, right? There are of course a deeper meaning to this, but not in this course. Okay. All right. So what should we use these for? We should use these to form encoders and decoders of binary block codes. Okay. So how do we do this? Well, then we, before saying exactly, there's one more thing actually, and that is polynomial division. Okay. So you know through your math classes that you divided polynomials before typically over the real field. Okay. So if you have two polynomials, you can divide them, you get a quotient, okay, and the remainder and the divisor. And everything works the same for binary polynomials as for regular polynomials, if you like. It's just that now we do all the calculations modulo 2. So just to say, binary polynomials can be divided just as regular polynomials. We can always represent a polynomial as a product between the divisor and the quotient plus a remainder. So if we have a polynomial p, let's call that the dividend. Then we have a divisor g and a quotient q and a r, which is a remainder. So these are all polynomials. And there is a unique, given a p and a g, given p and g, there is a unique q and r that satisfy this, where r, the degree of r is less than the degree of the divisor. Okay. It's just that like a regular, 7 is 3 times 2 plus 1, right? Same thing. Right. Where the remainder here is less than the divisor, which was 3 in this case. Okay, so if g, the divisor, is non-zero, which is the interesting case here, then we can write p divided by g as the quotient q times the remainder divided by g, just as before. So it turns out that doing this type of polynomial division is actually very easy to do in hardware. So you can do that with shift registers and binary gates and things like that. So it's actually a pretty neat type of math when it comes for hardware implementation. So it's not very difficult to do this, which is then of course the reason why we're interested in this from the beginning, because we want to have something which is hardware efficient. Okay, so we can find this quotient and this remainder. Either we can do it by hand, which we do now in the class and on the exams and things like that, right? In practice, of course, you have machines to do this for us. So we can do that by long division by hand or shift register by electronics, and there's very, very simple circuits for that. Okay, so let's see now. Let's get into cyclic redundancy check codes. How do they work? Well, remember, we have k bits as the input to the encoder. So we have D, which is k bits. And then we want to produce a code which has a systematic code which has the D bits from the beginning and then P parity bits, where P is n minus k bits. These are the parity bits. Okay, so that's what we're aiming for. So give me k bits and I should give you p bits. I should give you n minus k bits, the ones which are in the parity check. Okay, let me take that once more. We would like to find something that takes the information bits and produces the parity bits. That's what we want to do. Okay, so an nk CRC is defined by a generator polynomial g, which has degree n minus k. Okay, so n minus k is the number of parity bits. Okay. Now, G here actually represents n minus k plus 1 bits, but that's no consequence here. So G itself is not n minus k bits. It's actually, I shouldn't even have mentioned that. So forget about that. It's just a trivia thing, I guess. So we have k information bits, and they're represented then by a polynomial. Let's call it I for information. Then the n minus k check bits are represented as the remainder found by dividing x with g, where we first have shifted in n minus k zeros into the I polynomial. Okay, so we increase the degree of I by n minus k. Okay, we'll go through an example here to show how this is done in practice. But what we want to do then is that we would like to take the information bits and we would like to produce the parity bits. And the parity bits are represented by the R polynomial. How do we get the R polynomial? Well, we take our information bits and we multiply that with x to the power of n minus k, shifting in zeros in that polynomial. And then we divide that through the generator polynomial. And the generator polynomial is different for different codes. It's something which is given to us. And then, as a matter of fact, we really don't care about the quotient here. It's just a byproduct of the calculation. What we want to do is go from information bits to parity bits. These are the interesting relationship. Actually, this is the parity bits that we would like to compute. Okay, so how do we do this? Well, the code polynomial, the code word, consists then of the information bits plus the parity bits. Okay. So the first n bits in the polynomial is carried by the information polynomial times x to the n minus k. So it shifts it to the left a little bit. And then it leaves just enough space to put in the remainder polynomial after that, where there are no common powers between the remainder polynomial. Sorry, I don't want to do that. There are no common powers in the remainder polynomial and this polynomial, because we shifted to the right n minus k positions, and the degree of the remainder polynomial is n minus k minus 1. So it just fits very naturally in there. Okay? So this was a lot of information in short time. So just go home and look at this and be comfortable with the degrees and things like that. Then and check your understanding for how many information bits do we have? K bits. How many bits should there be in the code word? N bits. How many parity bits should there be? N minus K bits. Just make sure that you have the degrees right here in your head. And then let's make an example to show the actual calculations that we need to do. Okay, so it's N minus K check bits. Should there be N information bits? Of course not. It should be K bits. And the code polynomial should represent N bits. K bits in, N bits out, and the parity bits is N minus K bits. Okay. Shall we go on? All right. So let's do a calculation here. So somebody told us that we should use this generator polynomial. There is one unique generator polynomial for each of these CRC codes. There is a bunch of those, many of those. But this is somebody told us, okay, this is the generated polynomial you should use. Okay, so it's a degree 3 polynomial, which means that it's represented with 4 bits. Okay. The information bits is the input to our encoder, and these are the bits. I don't write it out as a polynomial. But then the first thing we should do is to, since we have a degree 3 polynomial here, we need to multiply the information bits with x to the power of 3, because this leaves 3 zeros at the end of the bits here, and this is where we eventually will put in the remainder bits here. Okay, and since we are dividing with the degree 3 polynomial, we have a degree 2 remainder polynomial, which is represented by 3 bits. Okay, so one of the difficulties here is to go between degrees and the number of bits, as you see, right? Because it's one is one more than the other, back and forth, back and forth. Right? Okay, so let's do this. And let's do long division. So we start by taking I times x3, and we just write out the bit pattern corresponding to that. Like this. And now we will start to divide by the generator polynomial. And we do it the following way. The first thing we do is to put the generator polynomial. We see where the first leading one of the information polynomial is, and then we align the bits of the divisor there. Okay, and then we add this modulo 2 as we've done before. So what's the result then? Well, the result is that 1 1 is 0, 1 0 1 is 1, 0 1 is 1, 1 0 1 1 is 0, and then we just copy the rest down here. Okay, so that's step number 2, and then we repeat. We put the generator polynomial, align it such that the leading ones are just above each other, and then we add modulo 2, and then we get a result here. And then we continue. And in the next step, we got lucky because, no, we didn't get so lucky actually. Here I think we will get lucky. Because here there is a nice match between the ones here, so we don't have to repeat this for so many steps. And we just keep on doing this until we're at the end, which is here. Okay, because now what we have done is that the leading one in what's left here is here, and we cannot fit 4 bits of the divisor beneath it. Okay, so then this is the remainder. And these are the bits we were looking for. Okay. Okay, so the result of this calculation is that the quotient is these blue bits here. We don't care about the blue bits. I just put them here to be, consistent with the division algorithm. We don't care about the quotient. We care about the remainder, because the remainder is what we will stick in as the parity bits in the code word. So the code word itself are the red bits, that is the information bits, plus the remainder bits, which are the parity bits. Okay. And that's it. That's how we do CRC encoding. Okay. So just to repeat, we need a generator polynomial, and we need an information bit polynomial to get started. Okay, so this one defines the code, and this is the input to the algorithm. The output to the algorithm is the remainder. Once we have the remainder, we can stick the remainder at the last bits in the code word. And since it's a systematic code, the first bits in the code word is simply the input. Like that. Any questions? Okay, so these CRC codes are rather powerful, have a nice hardware implementation, and is very, very often used in practice for error detection purposes. Very, very seldom, I don't know of a single case when it's used for error correction. So this is a code which is tailored for error detection. Right, so it's very specific for that. So any questions before we go on a little bit?
Is the same thing done in the receiving end?
So the receiver, well, let's see if I have a slide on this. Let's see. Sorry. I didn't write this down, but let me do that on the whiteboard instead. Let's do this maybe. Oh no. So here we go. Okay. So the code word is then xn minus k g of I of x plus r of x, like this. Now, if we then okay, and I of x is, let's see if I can do this by hand. So let's bear with me if I make a mistake here. So this is equal to g of x q of x plus r of x, like this. So then we have if we put this in there, what happens then? Let's see, we should have that c of x. This is what I would like to see later on, that it could be written as g of x times a polynomial q prime of x, like this. So it's divisible with okay, which has a zero reminder like this. So what we do is that at the receiving end, we go through the same process as we did here with the encoding, but with c instead. And then we see that we get an all zero remainder. Okay, so this is the way we do decoding. Okay, I'm unable to do this now because I don't have my notes with me, and I will probably mess it up. But let me get back to that, if not after the break, on Thursday.
So if you get all zeros, then there is no error?
No, but if you have if it's like this, if this relationship holds, that means that c of x is a code word. Okay, so the only thing you can check at the receiver is whether the pattern that you received is it a code word or not? If it is a code word, you say, okay, things probably went well, so I will accept this. If it's not a code word, you're sure something went wrong. So it's the same thing as before. We can only check, and if it's not a code word, we know something's wrong. If it is a code word, let's assume that things are okay. But there could be an error that had occurred, but it's undetectable. Okay. So let's. These animations are a little bit tedious. Okay, so just to finish off CRC codes, these are heavily used in practice, and so they're standardized, and there are many standardized CRC codes. There is this called SSY305. Okay, this is the polynomial, and it's used in all of these things, including Ethernet. So it's quite used in many standards. There is a 16-bit CRC that looks something like this, the polynomial, and it's used in these standards. And the CRC1, which has a very simple polynomial, this is actually the single parity check code, single parity bit check code that we talked about last time. So basically, the simple parity check is a special case of CRC, a very weak CRC, but anyways, right? Okay, so it has generated polynomial 2 with degree 1, which means that there's 1 parity bit. Okay. Source for this, you can look at Wikipedia if you like. If you do that, then they list the polynomials here, what they call the normal form, which means that they ignore the leading one in the polynomial. So if you look at on Wikipedia, you might not see these bit patterns, but I adjusted it to the notation we used in this lecture. All right. So if we want to summarize what we know about error detection codes, these are used for the receiver to detect whether errors have occurred or not. It's not a perfect process, so we need good codes for doing this. Basically, we would like to minimize the chance for undetectable error patterns to occur in the channel. And it depends a little bit on the type of error models that we assume, whether these are completely random errors or if there is some structure to the errors. There are 3 basic things: the parity check code, single parity bit like this. There's the internet checksum that we talked about, and then there are the CRCs. In addition to this, there are many other ideas, but these are the 3 main ones and the only ones that we will talk about in this course. So what we will do starting from the next hour here, we will assume that we have error detection codes, and we will assume that they work, right? So there will be some failures, but we will mainly assume that we can do this error detection and that it's no errors. There is no undetectable errors in this. And then we will comment a little bit what happens in practice, because of course there are undetectable errors, and we will later see that, talk a little bit about this and see that we do protection for errors at different layers. And we catch the vast majority of all these events. Okay, so let's take 15 minutes.